and we're going to continue with the Redpanda. Alexander Gallego is going to tell us about, I would say, design principles for building performance software, which is something that I think we haven't focused a whole lot previously, but it's an area where I believe deserves a lot more attention. It's the best way to not have to fix performance is to design software in a way that just makes it fast from the beginning. So looking forward for the Alexander's talk.
Everyone, my name is Alex. I am going to be talking to you guys about Vectorize, a new storage engine that we just wrote. This is for the Performance Summit 2020. So a little bit about me. Like I mentioned, my name is Alex. I am the founder and CEO of Vectorize. I've been in streaming for about 12 years. Prior to starting Vectorize and working on the storage engine Redpanda, I was the CTO for a startup in New York called Concord. We were a C++ stream processing engine. It's similar to Apache Flink or Spark Streaming, but we wrote it in C++ on top of Apache Mesos. We sold that to Akamai in 2016. And so this is sort of the only product pitch, but I need to give you context about what we're actually going to be talking about. And the remainder of the presentation for the Performance Summit is going to be exclusively about that last bullet, the 10x faster and Kafka-API compatibility. But let me give you context. Redpanda, the product that we build, is a real-time engine for modern applications. And so you can think of it as a Kafka alternative. And we focus very heavily on three things. One is operational simplicity. So we are one binary. We wrote it in C++. No data loss. So we use raft. We're not going to get into too much of the data loss guarantees. If we have time, I do have some additional slides at the end of the presentation. But the bulk of the presentation is going to be about how do we architect and what sort of the design trade-offs from the engineering front that give us at least 10x faster. The agenda, we're going to talk about why we wrote a new storage engine, like why not use Pulsar, why not use Kafka, why not extend an existing storage engine, why don't we just take let's say Apache Arrow as a format and then have streaming rights there or things of that nature. Or like why not, for example, write enough heap JVM storage engine and then plug it into this existing infrastructure. So I'll tell you why. We're going to give you a background of what problem we're actually solving. And the focus of this presentation is actually going to be on the low-level architectural primitives that allows us to build, to get better guarantees out of a new storage engine in terms of latency and throughput. So the million-dollar question, why write a new storage engine? I think it's easier to just to show people a graph so that you can contextualize yourself on the reason why anyone in the right mind would go and build an entire new storage engine from scratch. We recently actually made the code source available under the BSL license on GitHub, so definitely check it out at the end of the presentation and hit me up there if you have any questions. But this is why, right? The fundamental difference is that you can get up to 44x state latency improvement. You can, when you do, let me give you orders of magnitude intuition here. When you do something 2x better, 3x better, that means that you did something smarter. You took an algorithm and you improved on the algorithm and you just made it better. Anything that is above 10x, it's really kind of a fundamental re-architecture, and that's what we've done. So that's why we require, it's why we went and we tried to build the new storage engine. So a little bit of a background about what is the actual problem that we're trying to solve. In order, we're building a distributed order, immutable, and reliable chain of events. So an immutable chain of events, that one is really easy to understand. You show up to a restaurant and you write your name, let's say online, right? Because there's a few people ahead of you, so you write your name. That doesn't change, right? Like at the time that you write it, like that was it. It's a fact. And so this kind of immutability is really useful to build on systems on top of, right? Sort of a foundational way to how to reason about architecture. And there's actually an entire trend about this idea of event sourcing, where you produce and you react to little events that are happening throughout your infrastructure, and you kind of build higher level primitives on top. We are building something that is reliable, and by reliable, I mean it can survive particular kinds of failures. So for the system that we chose, we chose a quorum algorithm. So we chose raft as the replication protocol and the algorithm that defines our availability and consistency. We are a strongly consistent system, and we can tolerate F failures given 2 F+1 computers. So out of 3 computers, you can lose 1 computer and things will function as normal. If you lose 2, then you are unavailable. But it's reliable against surviving this kind of failures, right? So machine failures, and you can survive crashes too. It is order. And so order is when we start to level up the abstraction to the application, right? It means that if you send and you get acknowledgement for 1, 2, 3, it is always going to be 1, 2, 3, always. There's not going to be another ordering in which you happen to, like, permute the events in a weird order such that you get 3, 2, 1 or something like that. And it is distributed because the same series of events, 1, 2, and 3, live on multiple computers, right? So you have multiple copies of the same data on multiple computers, and this is to survive machine failure, for example. The context and sort of the lens that you, while watching the Performance Summit, should have in mind is hardware, right? And so I'm going to mention kind of the evolution of hardware. And in passing, I'm going to mention the innovations of software in time and see how they match up or not match up, right? So kind of the biggest 2 projects today really are Kafka, which is by far sort of the largest streaming system that we see in the wild, followed by Pulsar. From the customers that we speak with, I would say about 90% of users are using Kafka, and some other combination of them use Pulsar and NAT streaming and other projects. But I would say Pulsar and Kafka are sort of the main 2 open source projects out there that are doing streaming until last week when we came on the scene. So the innovations, each of these softwares had particular innovations in the streaming space. So around 2010-11, when LinkedIn released Kafka, they were really trying to take advantage of cheap disks, right? So spinning disks. They got the API right? So developers love the Kafka-API. They hate operating Kafka. They hate managing Zookeeper. They hate kind of like the operational complexity of what it means to tune and operate this particular system. But they love the API. They love that you can plug in TensorFlow followed by some SparkML and then plug it straight into Elasticsearch, and you have a super sophisticated fraud detection pipeline. That was really sort of the main innovation for Kafka. RabbitMQ, what it did, it was working with the, I think, AMPQ style message system, and it was this relatively liberal open source license. I think they used a Mozilla license, and it was really trying to compete against the big guys back in the day, TIBCOs and Solas and that kind of infrastructure. Pulsar added the disaggregation of compute and store as a sort of primitive to the streaming, right? And so the context for Pulsar is that it came out of Yahoo, and when you run sort of like specialized machines for storage and specialized machines for compute, you actually the total cost of running the system is cheaper. Of course, outside of companies that had big HDFS deployment, S3 became the disaggregation of compute and store, and that's thus the rise of the snowflakes of the world. But what happened in the real world is that hardware changed, and so the platform in which these software systems were built fundamentally changed from underneath them, right? So over the last 10 years, there was this massive performance improvements on the hardware. The first one, well, not as significant as the second bullet, that individual cores got about 3x faster, so higher frequency per core. So nothing relatively material, is still a big improvement there. But the material improvements really came from that the fact that there are taller computers, and you can now go and rent a machine on AWS, the i3E and Metal instances with 96 cores, right? And so the machine types that exist today that are readily available for rent on any of the public clouds can have up to 20 more cores than the machines that you were able to rent 10 years ago or so. But more fundamental for this conference are really three things. One, disks got about 10x cheaper, and so you could buy about a terabyte of SSD for $2,500 10 years ago or so. And now you can buy that off of Amazon.com for $200 per terabyte, right? So huge savings there. And the more important characteristic for as a performance engineer is the fact that NVMe SSD devices are probably over 1,000 times faster, not 1,000%, but 1,000 times faster than a spinning disk. That's such an architectural departure that is really almost hard to understand what is 1,000x faster. And at the same time, you could go and rent computers on all of these public clouds that give you 100x higher fatter pipes network throughput, right? And so the machine types that I was renting 10 years ago when I started playing around with the clouds were 4 vCPUs, maybe a gigabit of network transfer, and you were doing cloud 10 or 12 years ago. Now, like the i3E and Metal instances on Amazon are incredible. You get real measured 100 gigabits per second guaranteed on these computers with 10 terabytes of NVMe SSDs and 620 gigs of memory. And it's all just readily available on these cheap clouds. Let me give you a different view on what this means for storage systems in particular, right? And so a big part of the intuition about why we decided to write a new storage claim, remember the 44x graph, is that the CPU became the new bottleneck. And so, over 10 years ago, like spinning disks were slow. And, there's an entire category of algorithms really to trying to optimize how to read and how to write and how to manipulate the sectors on the SSDs. But NVMe devices are so fast. I think that the latest NVMe, the PCIe 4 spec can push 16 gigabytes per second from the motherboard to these NVMe SSD devices, each of which can handle 9 gigabytes per second, right? Readily available on that you can buy. The reason, though, computers feel faster on a per core is really sort of this true advances in instruction level parallelism. And so the idea here, think of the CPU actually as a network of microservices. And there's out of order execution where you have an addition and a subtraction and maybe a store and maybe a division, and you kind of fetch you can sort of figure out what would be the sequence so that the program output is the same, but you can start to execute non-overlapping instructions, for example, right? So if you have 2 additions and they're non-overlapping, then you can dispatch them in parallel. The next big one that helped CPUs feel faster and computers feel faster was instruction prefetching. There's each of these bullets is such a big and important topic that I'm just kind of gonna highlight the reason why these are useful for a storage engine. Branch prediction is really a big one, right? And so as you're executing some part of the code, there's 2 bits that are kept in cache that says like, oh, should I take left or should I take right, or should I reset the branch? That sort of makes the CPU magical. It's like it can literally predict your intentions as a programmer, executing on hardware you didn't even know existed. But really, for storage engine, I think the instruction cache is the Achilles heel of big software systems, and data caches the sort of dictate at what speed you can actually go through the data that you're trying to process. In our case, store, checksum, and shove around the network and so on. Again, those kinds of optimizations, coupled with the fact that hardware fundamentally changed from underneath all of these software systems, gave us the intuition that we could do better. That there was an opportunity to build a new engine designed from the ground up for streaming writes and streaming reads, right? So we have a very purpose-built engine that solves that sort of real-time stream, that real-time pub/sub system, and the performance impacts are incredible. This is a different view of the same graph. I'm gonna kind of walk you through the same arguments and in multiple and show you different graphs that are really all come down to the same thing. This is perhaps one of the things that we feel the most proud of. It's actually the deterministic latency, right? The fact that we sacrifice a little bit of the average case on the lower tier so that you can have predictability in your system, because once you have predictability in your systems, you can then reason about how to build products on top of this. So let's go on with the lower level architecture. And I hope that as when you're listening through this presentation, you have now a rich set of questions as to like how is this possible, or like how would I go about doing it versus what I'm about to present, which is fundamentally everything has to be asynchronous, and asynchronous scheduling in particular. A different approach to software building, which is a thread per core architecture, and then sort of a big performance improvement that we had over not using something like gRPC or Thrift is a custom built RPC for our storage needs. And I have graphs and sort of metrics for all of this. So let's talk about treating everything like an asynchronous network call. On the left, you have a dual socket motherboard. And so in the physical world, there's actually this giant separation of both, speed and protocols and coherency, just to send the message from core 1 to core 144, right? And then on the right side, you have this NVMe SSD device, which is pretty much a state of the art, right? So if you benchmark a recently bought laptop, you can probably sustain 1.1, 1.2 gigabyte per second sustained writes, unless you're in the PCIe 4 camp and one of the latest NVMe SSDs. But most laptops are probably around, let's say a laptop bought it within the last 3 years, are probably around this range. So incredibly high bandwidth for this NVMe device, but the latency to issue a single page write, right? So an average latency, and let's pause this for a second, is probably on the order of 20 to 140 microseconds to write 4,096 bytes via DMA to one of these devices, which means if you're waiting, right, if your program structure is such that you say f write followed by print and followed by an f read, right, between that line of code, you just wasted up to 420 million clock cycles, like gone, thrown in the garbage. And so this is really sort of telling about why it's important to build with asynchronous scheduling primitives. And the Linux scheduler now has the IO ring or the libaio with the polling drivers that you can sort of tell the Linux scheduler, hey, go do a bunch of work, but don't interrupt me. I'll come back and I'll rip the events when I'm ready in the next loop of my program. when thinking about how to build an asynchronous first storage engine, it's sort of you have to pick a threading model. And the threading model that we picked was a thread per core. In particular, we leveraged this excellent framework called C-Star. And C-Star is a framework that is async only, not just first, but I mean only, as in like if your program, if a single function call takes more than 500 microseconds before it cooperatively yields by wrapping the result into a future structure, the reactor, which is this while true loop, will literally stop spamming your logs and telling you, by the way, you're blocking and propagating the latency all the way up to every other subpart of the system. And so what a C-Star future is in particular is really this viral primitive. And it is viral because it is driven by this reactor stall, right? Like you have to understand the machine and understand what is the impact of holding a particular unit of execution, let's say a function, for longer than 500 microseconds. What you're saying is that you're willing to propagate at least 500 microsecond latency to the pollers for IO or every other subsystem, or hold every kind of progress. And so what ends up happening is that you wrap every other computation in a future. When I was programming in Akka 8 or 9 years ago, when you introduce an actor system, everything becomes an actor. It is sort of this thing is just like everything it touches magically turns into an actor, because it's easy to deal with asynchronicity as a first-class citizen in your storage engine than it is the alternative, right? The alternative is you issue this F write and you might block for God how long, sometimes actually multiple seconds, depending on how busy, you whether you happen to hit a page cache flush followed by a stall on the NVMe SSD because everything is full and so on. So whereas if you embrace asynchronicity as a first-class citizen, you end up focusing on the concurrent structure of your program, which means parallelism becomes a fee variable. That is, that the correctness of your program does not depend on the number of simultaneous execution units. And so to make it more real, a simultaneous unit of execution, in particular in the C-Star framework, is a thread, right? So a P thread, like you do P thread create and you run it, that's it. That becomes a parallel unit of execution. And futures allow you to write your program with structure such that if you happen to have more CPUs, you get this free variable about the simultaneity execution of your particular program. In a visual representation, this is roughly how it looks. And underneath its covers, there's actually a network of SPSC queues, single producer, single consumer, for those listening in. And so in this graph, you'll see core 0, for example. This magical machine only happens to have 3 cores, but core 0 will have 2 outgoing mailboxes for core 1 and core 2, and the same thing for the other cores. And so this polar thread that I've been talking about with this framework does sort of checks the mailboxes, each of the incoming mailboxes from the other cores, and then does IO, and it rips both IO on the network and on the disk, and then executes your futures. And these futures are really cheap to have. You can have millions of futures per core and be just totally fine. 2 things to highlight is that everything about asynchronicity, because it's really such a raw and first class and really in your face as a programmer, becomes explicit. And the impact here is you can see is that C-Star sort of really allows you to scale pretty much linearly. There's like some sublinear factor on the high end number of cores, but mostly linear as you increase with the number of cores. It has some downsides. The first one is so it's in C++, right? So there's no other framework. And because everything becomes a future, right? And everything is explicit, which is good as a way to bubble up latency problems from the disk all the way up to the RPC level. it sort of really looks like it's really hard to read sometimes. This is, for example, part of our raft implementation, the append entries call. And two things to note here is that even communicating to a remote core, because everything is asynchronous and explicit, you attach how many shares can I use to communicate to the other core, so that you can start to prioritize background and foreground work. And so it's really fundamental, right? It is a choice that we made on the threading framework, followed with an excellent IO priority scheduling and cross-core CPU communication that the guys at Sistar wrote. Three more things to highlight in terms of like how we went about building this is the thread per core I've kind of talked about at length. From the point of building the product, which is Redpanda, we divorced the external API, which was Kafka, from the internal API. And the reason for that is that the cost of translation, the first thing that we wrote was using a previous open source project called Smurf that was using Sistar with flat buffers. But we actually found that the cost of translating between flat buffers and internal data structures was too high. It was something like 7x for deeply nested structures. And so we built our own RPC framework that is, it's custom, right? So no Thrift, no gRPC, and this goes against maybe some common wisdom. But this was actually a really big performance strategy for us as we started to build the new storage engine from the ground up. The intuition here is that for a storage engine, the majority of the payload is a small materialization of data, metadata, which tells you, what topic or what the table name is, what partition, what permissions do you have, a couple more metadata, so some integers maybe, but then the majority of the payload is this blob, right? Like your point as a storage engine is literally to move bytes between one place or another and do it reliably. And so with this observation, we decided to rewrite our own RPC. I'll talk briefly about leveraging direct memory access for reads and writes. Remember that our problem is not generic. What we're building is a real-time streaming storage engine. So we have a particular problem and domain expertise where we can build custom algorithms for the read ahead and the write behind strategies, which is how it works on the Linux kernel. There's like a very sophisticated read ahead and write behind when you issue an fread or an fwrite. But we can embed particular knowledge on the caching hierarchy so that we can deprioritize cache pollution from different actions of the storage algorithm. So the purpose-built algorithms, we found it to be around six times faster than flat buffers, which is really mind-boggling given that flat buffers is just a little Indian encoding with the virtual table dispatch. And so the reason for this is that, like I mentioned, the majority of the payloads for a storage engine is just this small metadata object followed by a large blob. And let me just show you the graphs for really large payloads. We actually doing it the way we did it was a little bit worse, but for payloads that sort of average storage size request, so let's say less than 1 megabyte in requests per fragment, right? So per batch, we found that it was around around 7x faster than just using flat buffers internally. And the reason for this, though, by the way, is that we sort of hook into the low-level allocator on the storage engine, and we optimize for this large blob. And the way the physics work in terms of the network throughput is that when somebody's sending you writes, it's not like they send you a single buffer of a gigabyte of data. They literally start sending you these fragmented buffers, these fragmented chunks. And so what we did there to achieve this 7x faster is that we optimize for that case. And then we say all our buffers are fragmented. And this is how the Linux kernel works too with, I think it's called kbuff, maybe in the FreeBSD kernel. mbuff is in the FreeBSD kernel. And I think maybe kbuff in the Linux kernel. The idea is that you have this chain of objects, right? And so an array might be 1 kilobyte, the next array might be of bytes might be, I don't know, 20 kilobytes, the next one might be 500 bytes and so on. But instead of linearizing the memory and putting pressure on the allocator to find a linearized and contiguous amount of memory, you're just really taking advantage of the runtime performance that your application is going to have a lot of memory fragmentations the longer it runs. So instead of forcing the allocator from doing a bunch of work and reallocating arenas, we just said, just give me space as you have it. And it makes it sort of really friendly for machine saturation in particular. We don't have too much time left in the chat to talk about the kind of purpose read ahead and write behind. The intuition behind this slide is that because we have a custom built a problem that is very specific, right, which is a storage engine. It's not a generic IO scheduling algorithm that is catered for streaming reads and writes. We could do better than the generic Linux kernel page cache can do. And in particular, we can exploit sparse file system support and a custom IO engine to, in this particular graph, is we have 4 buffers and we can actually dispatch them out of order. And so we align the memory on the application such that we can actually concurrently, actually in this particular case, let's say if the NVMe device happened to have 4 queues, you can actually finish these things in parallel as well, right? So there's sort of a very fine balance between here and concurrency and parallelism. But the point is that we submit it to the Linux kernel concurrently, and the NVMe device might finish them in parallel. But out of order is such a big sequence, which means the last buffer we dispatch might happen to be the first buffer that gets written on the NVMe device. And that kind of low-level exploitation about how the physical hardware works is what allowed us to get that 44x tail latency performance improvement. From an architectural design, and we have 4 minutes left in the talk, is we have this nested ring structure where we bootstrap a raft ring with just configuration, and then that'll bootstrap every other partition creation. And so perhaps kind of to sum this up about, and make it practical for those that are listening to this chat, is let's walk through the physical execution of what happens when you submit an RPC call to Redpanda. And so the first thing that happens is you submit it to this RPC decoder, and this is again, we parse the bytes at the TCP level from all of the Kafka clients. So this is not the internal API. I have a slide coming up for that. This is the external API. But what this thread per core architecture forces the programmer to do, so this is not all rainbows, is that it forces you to materialize data structures that are thread local to the cores that are handling that request, or to make it explicit about which core handles the data, and to make an explicit remote core structure message pass through this network of mailboxes I mentioned in the beginning, and then transfer sort of the flow of execution to that particular core. So it really sort of inverts some of the design patterns where you simply have a global cache and you push a barrier, you push a barrier, you write some data, and then you push then you flush that, and then you release the barrier, such that every other core has this global coherency about what this particular data structure is. There are some patterns that are simply more difficult, where you have to do upfront design work to understand what is the memory impact and how you would go about saturating a particular hardware in the way that you're designing your data structures, right? So for our design, and this is on GitHub, so you guys can go on and read it, we actually materialize particular views per core lazily. And then core 0 has really the ultimate source of truth. And so there's this lazy metadata materialization for raft. But then to follow the full flow, core 0 would send the data to core 1 via this mailbox. Core 1 raft, which is our consensus algorithm, would pick up the message and via this network of SPSC queues, and then would eventually write it to storage, and the same path flows back. Notice that there is no direct communication between core 1 and core 0. It all happens through these networks of SPSC queues. And what's important there is that then you can prioritize both IO and work and scheduling, and it gives you a useful primitive. So this is sort of the fundamental data structure that we chose and how we decided to build a new storage engine from the ground up. And I kind of walk you through the entirety of from the lowest building principles into now having this. And this is the last slide I'll cover, technical slide. So we have 3 minutes left. Is now imagine that core 1 on the first computer has to send the data to two other computers. Because they sort of all look the same, a similar flow happens on this remote destinations. And remember that raft can survive F failures given two F+1 computers, which means it's a quorum system, right? And so when you actually issue a write from the Kafka client, let's say you have a Java or C++ or Go client, it'll first land on core 0. It'll go through a metadata materialization step that is core local. So this is super low latency, right? This is materialized on the core that happened to receive the request. And there's some data that is materialized on every core that looks the same. And then there's a core routing algorithm and mechanism. But then when you dispatch it to this other remote cores, this asynchronous sister feature is this really sort of nice building block to treat everything like a network call. Whether you're replicating across network or you're sending a message to the next core, the latency that core 0 experiences is sort of the sum of the latency of the all parts for this particular write request. And so it allows you to build up applications quite nicely in a way that gives you sound primitives, a sound both concurrency model and a sound parallel execution model. With that, I'll end it here. I just want to highlight, please reach out to us on Twitter. I'm Alex at vectorize.io. If you want to send me an email, reach out to me on Twitter or on the main account or on Slack if you want to have questions about this. But most important, the entire contents of this talk, it's all in a source available GitHub repository. So definitely check it out and let me know. All right. Thanks, everyone.
An awesome journey, how you built this amazing storage engine. It's like one of the reasons why we always wanted to have this event, a mix of different types of platforms and approaches, because I believe that there is just so much to learn from each of the adjacent platforms. Like in, for example, www world, it's been always the case where you had to have everything asynchronous, and you have to rely on event loop and make sure that you don't block the main thread. It became the same sort of requirement for mobile devices, and now it looks like you benefit quite a bit from the same architectural decision in Redpanda. And so since this pattern becomes so prevalent across pretty much the entire industry, I'm curious if you have any advices or suggestions to anyone who is trying to build an application, mobile application, or like web application, or even a service similar to yours. How can they benefit the most, or whether they even should embrace this asynchronous model?
Yeah, you know what is interesting there even is I didn't have a chance to cover it at length there as well, was actually that trend of the rise in core count and not the rise in per CPU frequency is only going to continue. Like if you even look at the GPUs, is basically what it is. It's just a network of thousands and thousands of cores. Slightly different latency models and throughput models for your coherency, which means like how do you get two CPUs to do something useful? But when you start to measure latency on multi-socket multiboards, where you actually have some silicon and two CPU sockets, the latency on a contended resource across like two NUMA domains is actually comparable to a network call via a relatively fast network link. And so what's sort of fundamental is that whether people embrace it or not, that's just how hardware is working today. And so I think what is useful from application builders and people that are trying to build services is really to understand that that's just how the hardware works, and one way or the other, you're just going to have to execute in it. And in a way, what we did that was different was really just to embrace the real world, right? I mean, I think one strategy is you use an abstraction layer like the JVM, and it's wonderful. It sort of really allows for rapid development of applications, but it hides too many details. And I think there are some details for performance-oriented products where performance is not just a feature, right? It's sort of like it is a fundamental part of your product. And when you're trying to replicate a petabyte of data per day, which was sort of the internal design of Redpanda, paying attention to sort of how hardware behaves fundamentally, has this huge payoff. So if people are looking to embrace not embrace asynchronicity, I think that's fine. There's definitely tasks for it, like, orchestration layer things. They don't need to be fast. They happen within human time. But when you're dealing with compute time, when you're dealing in the realm of probably single-digit microseconds, to let's say 100 microseconds, when you start to understand what can the hardware do, and when it becomes cost prohibitive, then I think there's there's really no alternative. And Rust and C++ are really trying to tackle this from a language perspective, with at least in C++ with coroutines landing in C++20, and there's other programming frameworks that sort of help you organize your code in a way that is composable, like Pony language and other actor frameworks. So I'm not sure that people will have a choice for too long. Like, if you're really trying to do performance work, if you're just doing, like mobile stuff, things that happen in the human time, then it's fine. Like, you really don't need to, like, single thread performance still insanely good. I think it's when you're trying to maximize your infrastructure that you're going to run into sort of the problems that we were trying to solve.
Yeah, mechanical sympathy all the way. In fact, I guess not many people frequently think about how cache coherency works, but it's actually message passing, and it's pretty much the same as RPCs and all that stuff. And in fact, it has quite a bit of associated cost, which is why the memory transaction model is built on top of cache coherency, just because all those messages communicate through the protocols similar to MESI. They're actually much more complicated these days, but it's the same idea. So embracing it and using it on the application level definitely benefits the applications, although sometimes it may be a little bit harder to reason about. And to what you mentioned about single-threaded performance, there was actually an interesting study at some point which compared the performance of Hadoop cluster doing some sort of processing versus single-threaded processing of the same payload. And the single-threaded was actually faster than the Hadoop cluster, just because the overhead associated with all the reading from disk, distributing the work, the scheduling, and all that stuff. So you have to actually be very, very much sure that the amount of data that you have to process is warrants the distribution, because the first law of distributed computing: don't distribute.
Yeah, it's true. Though what I think people are reaching out to is really the mental model. What is interesting is that we help the super large edge companies think like the largest CDNs, where they're trying to push 4 gigabytes unreplicated data per second. So 12 to 15 gigabytes per second of data with replication, so huge volumes per cluster. But the fact that you can use the same mental model from something like lower, probably in the hundreds of megabytes per second, to like that kind of volume, really sort of future proofs your software. So I think it is true, and depending on kind of like where in the performance spectrum you might be, I think it's why we based it on a thread per core performance. We have a use case where someone is running on a security appliance on a single core, but then they run the same stack in the cloud with like 7 computers, and each computer has 64 cores. And so there was a paper, I think it's called ANA Key Value Data Store, which is like sort of these primitives of how do you start to build this single threaded primitives where actually the simultaneous execution of your code doesn't affect the correctness, right? Because you've built sort of a structural correctness into your program, and then parallelism, it's a free variable, like I mentioned. And then you couple that with like a data replication model like raft or chain replication or whatever you want to use. It's nice in that it allows you to scale up from a single instance that is embedded with maybe a gigabyte of memory or 200 megabytes of memory, up to clusters with multiple terabytes of memory.
Yeah, it's fascinating research, and I actually hope that eventually it's going to give the same boost as things like CRDTs, where just by composing your data structures in the right way, you can converge them. I hope that we're using associative data structures to make sure that you can parallelize them, whatnot. So I hope that we'll eventually have the same set of primitives built in into most of the distributed systems. I would love to continue the discussion. It's just unfortunately we are criminally out of time. It's super unfortunate that you are not going to join us for the panel discussion, although you are very welcome to join if you would like to. So thank you so much again, and I wish you and Vectorize.io success, and please continue spreading the best practices in building distributed systems. It's really awesome work, and
Thanks for having us. I appreciate it.
Thank you.